In these sections, that is our first time to look into the three-dimensional formulations of Hooke's law. Since we have learned the definition of Poisson ratios, from there we will be able to deduce the change in dimension, which means we will be able to know the deformations in other two directions than the loading directions. So that allows us to explore the three dimensions deformation here. And the principle of generalized Hooke's law, basically we can take the superposition principle, which means because here in elastic deformation, everything is in linear the relation, so we are able to apply the superposition principle here. So with that one being said, and here we can look into a little bit more details. So for example, here we consider a deformable material. It is under loading in three directions, so that's the three axial loadings applied in individual directions here. So for each loading, we will be able to calculate the stress. So for example, here we said the calculated stress is sigma x, okay? And then this is sigma y, and then sigma z. And again, in equilibrium, that is sigma x, sigma y, sigma z. And we apply the superposition principle. Basically, we decompose into three subsystems. And for the first one is under the uniaxial loading, like this. So from here, we learned from earlier one-dimensional Hooke's law, the strain corresponding to this is simply the stress divided by Young's modulus. So this representing is the axial strain. So now for this case, y and z are defined as the lateral directions. Okay, directions. So through in which we are able to apply Poisson's ratio definition to determine the strain, the lateral strain. The lateral strain by definition is the Poisson ratio multiplied with the axial strain, which is this one. And always the lateral strain has the negative sign to the axial strain. We put a minus here. So we exercise one more time. This is the corresponding axial strain. We multiply with Poisson ratio. That is the magnitude of the lateral strain, and in z direction, and always that has the negative sign to the axial strain. We put a minus here. So now we calculate the second example. So now we say this is sigma y here. So in this case, right now y is the axial direction. So y is the axial direction, the axial strain, sigma y divided by e. So that is the axial strain right now happen in y direction. So again, respect to the axial direction, x is the lateral direction. So the strain, the lateral strain, Poisson ratio multiply with the axial strain, that is this value, and a sign is negative to the axial strain. In a similar way, z is the lateral directions in which the lateral strain is given by this, and again negative. Okay, so in the third directions, so this is sigma z. Okay, so this is sigma z. Right now z is our axial directions, so z is our axial strain. So stress divided by Young's modulus, so that gives us the axial strain. So the lateral strain in the similar fashion, this Poisson ratio multiply with the axial strain with a minus, Poisson ratio with the multiply with the axial strain, put a minus here. Okay, so right now we have everything, then we superpose. So basically superpose together, that means the total strain in x direction equal to those terms together. Okay, this term plus this term, basically the three terms add up together. Okay. In a similar way, the total strain in y direction is the summations of the three terms, 1, 2, 3 terms added up together. Okay, and then in a similar fashion, in the z direction, the total strain in the z direction is the three terms together. So that one come up with is this equation here. If you compare this one carefully with the previous page, okay, and I let you take a look at one more time in this page compared to this equation. I simply summarize the equations here. So this gives us the part of the generalized Hooke's law and described in 3 dimensions. This equation will appear when an object is under multiple axial loadings. Okay, and one feature is this: the strain simply linearly related to stress. Okay, that is the term right here. So this is part of the generalized Hooke's law to account for the normal loading. And the second half of the Hooke's law is to account for shear loading, and that will be in the following sections. And 3 normal loading equations and plus the other 3 shear loading equations. In total, for generalized Hooke's law in 3 dimensions, we have 3 normal loading equations, 3 strain loading equations. This one will be talked about shortly in the following section here. And we can look at one example. And for this case, we see, since this one we can simplify, we can just simply attack this problem by using the very simple one-dimensional Hooke's law, like we did back to a couple of lectures ago. However, right now we have more detailed, precise formulations in terms of 3-dimensional. Why not? Since we have a better tool, why not we use the 3-dimensional Hooke's law to solve for this problem? We see how much they can do. Okay, so the first one, we assigned our coordinate systems, and for example x, y, z like this. So under these situations, I want to highlight right now z is our axial loading. That are our axial directions, because in axial direction, that is in the direction where the loading applied. So that is where we define as the axial direction. So in this case, we can determine the stress in axial direction, that is 80 kilonewtons, and divide by the cross-sectional area, 100 millimeter times 50 millimeters square. Okay, so this one, let me do some calculation. 80,000 newtons millimeter square divided by 50/100. So cancel this one. So this is 16 MPa. So sigma z is 16 MPa. We determine here. Okay, and right now, for this case, we want to know the deformation. Basic deformation is equal to the strain multiplied with the dimension in x direction. This is the strain multiplied with dimensions in y direction. This one is the strain multiplied dimension in z directions. And individually, and the dimension in x equal to this one here, so that is 0.1 meter, and the dimension in y directions, so that is this one, so that is 0.05 meter. The dimension in z direction, that is 1.5. Okay, so here we have this one. So basically, to answer these questions, we simply need to solve for what is this, what is this, what is this, that happen just appear on the left hand side. So we want to solve for the strain, then basically we need to have everything done kind of the provided on the right hand side. For this case, the Poisson ratio equal to 0.32, that is given, and material properties, Young's modulus is given. So now for the remaining is we ask ourselves, what is sigma x? Sigma x is the stress in x directions. For this case, because we only apply the loading in z direction, so sigma x equal to 0. Okay? In the similar way, and y directions, and there's no loading applied, so sigma y equal to 0 as well. So under this case, we can completely solve for sigma and y and z, and then once you solve for those numbers, you simply plug in here, then you can obtain the deformations. Okay, we look at the second equation, the question here, the example here. So this one is a plate, a deformable plate that being sandwiched on his top and the bottom. So that is a constraint, meaning that there is no any displacement be allowed. And this material is under loading in x direction. So this is a side view here. So basically the loading right now is kind of the inboard or out of the board. Okay, that is sigma x. But you can see in z direction, in this z direction is free to deform. So we try to translate those given information to Hooke's law here, because that's the 3 equations. At most, we are able to solve for 3 unknowns. That means given 1, 2, 3 strains, 1, 2, 3 stress, and 3 stress, and 3 strains, and sorry for the interruption. We're back here. So here we have 3 strains, 3 stress, and only 3 equations. So we need to identify 3 numbers for 6 of the 3 of the 6 those things here. So the first one we see, and let me change the different color. So here we are sigma x is given. So sigma x is given here. Okay. So here you can see that is compressive. So basically sigma x is in nature, that's a negative number. But here we're using the symbol here. So that's the first one. Then the second one, you can see in y directions is no deformation. In y direction, the deformation delta y equal to 0, that indicating sigma epsilon y equal to 0. So this one equal to 0. Okay. And then what else? And in the z directions, this material is free to deform, it's free to expand or free to contract. So free to move, free to deform, that means there's no stress. So this one equal to 0. Okay, so given the 3 equations, right now we only have how many unknowns? This one, 1, 2, 3. We only have 3 unknowns with the 3 equations. Basically, we can solve for this one completely. Okay. Then once we solve for this is the deformations in z direction. So basically, this one is equal to the strain in z directions and multiply with dimension in z direction, that's t. Okay. Again, we use the strain equal to deformations divided by original length. So using this equation, we obtain this one. And sigma y, basically solve for this one, that should be no problem. Okay, so details, leave this to you. And this is another example here. So we still have the 3 equations and generalized Hooke's law. So again, we pick up the coordinate system like this. So here we are given the stress sigma z equal to 15. So this is 15. 15. I think this one is given certain numbers here. Okay. And then sigma x is also given, so sigma x is also given, so sigma is also given here. So I think looking at this number here, the sigma x equal to given, equal to 12 ksi, and sigma z is given 20 ksi. Then we are also given the Poisson ratio equal to 1/3. So put everything together, you have, in addition, what is sigma y? Sigma y can see in this direction, vertical direction, the material is free to deform. So this one equal to 0. Okay. So with sigma x, y, z, then you can complete the other two equations for strain x, y, and z directions. So that's detailed here.